In this lesson, we're going to focus on how to set up equations for related rates problems. We're not going to get around to solving them quite yet. Being able to set them up is a really critical skill. So for this lesson, we're just going to do the following. We're going to underline and label our rates in the problem. We're going to draw a picture and label variables and constants. So variables are anything that's changing, and these get a letter. And constants are unchanging, and the number should be given to us. We're going to make a knowns and unknowns table, write an equation that includes the variable we know the rate of and the variable we want to know the rate of. And we're going to stop there for now. In future lessons, we're going to work on taking derivatives with respect to time and then using that knowns and unknowns table to solve. But where I see students running into trouble oftentimes is that they go straight for trying to put numbers in and like the rates in and like, well, whatever. And no, the very first thing is just to make sure that you've got the equation set up right. So let's look at this example. We're just going to stop when we get to the fourth step above. So the side of a cube is expanding at a rate of 2 feet per second. What is the rate of change of the volume of the cube when the sides are 3 feet long? So underline and label our rates. So the side of a cube is expanding at the rate of 2 feet per second. So let's say the side of the cube is S. This is going to be ds dt. Where S is a side. What is the rate of change? It's another rate of change of the volume. So let's say this is dv dt, where v equals volume. Right like that. Okay, so second thing, we're going to draw a picture and we're going to label the variables and the constants. So we have a cube. And one of the things that we know about a cube is that all of the sides are the same. So we need to determine first of all what's changing and what's constant. So the thing is that right in here we're told that the sides are 3 feet long. But are the sides always 3 feet long? No. We're told that the sides of a cube are expanding. Actually, I think that should be plural. The sides of a cube are expanding like that. So that means that this should be S. This should be the sides like that. And in fact, we already labeled it with a variable here. So that indicates we're not going to put a number here. We're just going to label the sides. And there's nothing else really to go in there except insofar as we have volume on the inside. Okay, make a knowns and unknowns table. We know that the sides of a cube are expanding at a rate ds dt equals 2 feet per second. And one of the keywords here is expanding. So this is something that means that this side is getting bigger. And if something's getting bigger, then it has a positive value. And if something is getting smaller, then it has a negative value. And we'll see an example with a negative in a little bit. So a thing that is getting bigger has a positive rate. Shrinking equals negative. Rate. So that's a known. What is the rate of change of volume? That's a question mark, so we're being asked dv dt. And when the sides are 3 feet long, so we know the actual value of a side is 3, even though we're not putting that on here because the sides are changing. Okay, last step, write an equation including the variable you know the rate of. So that means we need to include s and the variable we want to know the rate for, v. So we need an equation equation relating S and V. Now, nicely enough, length times width times height is just side times side times side. So side cubed equals V, volume. And that's where we're going to stop for now. In later lessons, we're going to go on and see what do we do from there. Let's look at a second problem that has a negative value for a rate. So we see what that's like. So a fisherman is reeling in a fish that is on the surface of a pond. The tip of the pole is 0.5 meters above the water. The line is being reeled in at a rate of 0.3 meters per second. How quickly is the fish traveling toward the fisherman when it is 1.5 meters from him? Okay, so the first things we need to underline and label are rates. The line is being reeled in at a rate of 0.3 meters per second. So let's say L is the line length. So this is dl dt. How quickly is the fish traveling toward the fisherman? So this is a rate. Let's say F is the distance from the fisherman. So we want to know df dt. So let's draw a picture of whatever is going on here. So we have a fisher person, well, a fisherman it says in this case. Okay, and they're standing there. And there is a pond. So let's say they're standing on the edge of the pond here. And somewhere out there, there is a fish. Okay, there's a fish. And they're reeling in a fish, and so it looks like they're doing that with a fishing pole. So here is the little reel with the handle, and there's the fishing pole right there. Okay. And it says that well, there must be a line there that's attached to the fish right here. Okay. And the tip of the pole is 0.5 meters above the water. So the distance here to the surface of the water is 0.5 meters. And this isn't changing. So let's see, the line is being reeled in. So this is getting shorter. But the height of the pole above the water isn't changing at all. So that we can label with a number, 0.5 meters. The line is being reeled in. So the line length is changing. This must be L. How quickly is the fish traveling toward the fisherman? Let's see. When it is 1.5 meters from him. Actually, I'm going to change this problem up just a smidgen. 1.5 meters from the point directly under the pole tip. That just makes it a little easier to solve at this point. We could do it the other way, but we would need a little bit of additional information. Okay, so the distance from fisherman's pole tip here. So that means this is the point directly under. This is that F right here. It's changing. The fish is being dragged in this way. Okay, make a knowns and unknowns table. The line is, let's see, the 0.5 here is already labeled. Line is being reeled in, dl dt, at a rate of 0.3 meters per second. Now, here's the really key thing. This is being reeled in. It is getting smaller. That means that this is a negative. That's really important because otherwise we're going to mess up our answer when we go to find the other rate. How quickly is the fish traveling toward the fisherman? So we want to know df dt when it is 1.5 meters from the point directly under the pole's tip. So that means we're told that f equals not 0.5, 1.5. Okay, now we need to write our equation. And the key thing is we have to have something relating this and this. And the thing that you have to notice about this is that this here is a right angle. And it is because this is a point directly below. It's a vertical line. And this is a horizontal distance here. And a horizontal and a vertical line always meet at a 90-degree angle. 90-degree angles or right triangles are very, very common in these problems. So if you see something that looks like it ought to be a right triangle, it pretty much is. Otherwise, a lot of these problems aren't solvable. So that's typically what we see. I need something that relates the three sides of a triangle. And as it so happens, I know something that does. That would be the Pythagorean theorem. So 0.5 squared plus f squared equals L squared. And then in the next lesson, we'll see where to go from there.